Let's review free energy. The change in Gibbs free energy tells if a process is thermodynamically favorable, or not, in the left to right direction. This change for a process is defined delta G equals delta H minus T delta S. If delta G is less than 0, thermodynamically favorable left to right. If delta G is greater than 0, not thermodynamically favorable left to right. If delta G equals 0, at equilibrium. Standard free energies of formation, delta GF naught, have the value of 0 for elements in their standard states. For compounds, these values can be looked up. From delta G equals delta H minus T delta S, we see that delta G varies with temperature. If I read that statement in class, this is the look that I get. I try to clarify something along the lines of, when temperature changes, so does delta G. If we look at the equation, if we put a different value of T in, we'll get a different value of delta G. And then a few light bulbs turn on. This next statement is very important. Delta H and delta S change little with temperature. We just mentioned that delta G changes with temperature, but delta H values and delta S values don't change much with temperature. They do a little, but not enough for what we're concerned about. So let's calculate these values for this reaction. We're going to have to look some of these up. But are there any of them that we know without having to look up? How about for the standard enthalpies of formation? Are there any of those that we know without looking up? And that would be the one for oxygen, because for elements in their standard states, delta HF naught values are 0. How about the delta GF naught values? Again, for elements in their standard states, delta GF naught values are 0. How about for standard entropies? None of them are 0. They're all positive. And, in general, as molar mass increases and as the number of atoms in a molecule increases, the value of the standard entropy increases, and that is, in fact, what we see here. Now that we have all the values, what we're going to do is we're going to do products minus reactants for all of those to calculate those standard changes. So I've recopied from the previous slide our values. Let's show our work here. Delta H naught is going to be products minus reactants. We take the coefficients in the equation, multiply them by the delta HF naught values that we looked up. So 2 times 33.2, that's the products. We can skip the oxygen because it has a value of 0, minus 2 times 90.3. That gives us our delta H naught of negative 114.2. Is this exothermic or endothermic? And we say exothermic because that sign is negative. We do the same thing for delta G naught. 2 times 51.8, that's the product side, minus, again we can skip the oxygen, 2 times 86.7, and that number comes out to be negative 69.8 kilojoules. What does that tell us about spontaneity or not? Definitely spontaneous. Delta G less than 0, that is delta G negative, is going to be spontaneous. This gives us no information about the rate, but it does tell us that this reaction would be spontaneous left to right. The calculation for delta S is a little bit longer because all three of the substances have non-zero values. So let's check and make sure we've done this right. The products would be 2 times 240 minus, and then 1 times 205, so I didn't bother to put the 1 in there, plus 2 times 210.7, that looks right. Delta S naught is negative 146.2 joules per Kelvin. Is there more or less disorder at the end? And the answer is there's less. Check it out. In the equation at the top of the screen, we are starting with 3 particles, 2 NOs and 1 O2, and we're ending with 2 gaseous particles. There is less chaos, less disorder at the end. We want to estimate delta G at 400 Kelvin. Again, I've recopied the values from the previous slide, and right in the middle of the screen here, I'm circling with my laser pointer now, these are the delta whatever not values that we just calculated on the previous slide. The key here is to remember that delta H and delta S vary very, very little with temperature. Got a little carried away with my varies there, but frankly I did that on purpose. We're going to use the Gibbs free energy equation. The delta H value that we calculated under standard conditions still applies. The delta S value that we calculated under standard conditions still applies. Even though we're not at standard conditions, the delta H value and the delta S value that we calculated at standard conditions we're going to consider to be good enough. But we put our new temperature in, 400 Kelvin. We need to be careful here that we have the units correct. If you look right in the middle of the screen, these are the values that we calculated on the previous slide. Delta S naught, this is on the right side of the screen, is in joules per Kelvin, and delta H naught, this is on the left side of the screen, is in kilojoules. So we need to make sure, I'm looking down now 3/4 of the way down the screen at this work that I've shown, you can see that we've made sure that we have the units match up. Negative 55,600 joules, or negative 55.6 kilojoules. This would be a spontaneous process at 400 Kelvin, but again, it doesn't give us any information about the rate.